Hi everyone, welcome to week 12. We're going to be talking about a new kind of function, which is called an exponential function, which is also the last category or class of function that we cover in this particular course. This is a definition, function of the form b to the x, where b is a constant and x is any real variable. So the most identifiable difference from all the other functions we have seen so far is that in this case, the variable is on the exponent instead of being on the bottom. This is called the base, right? And the top part is called the exponent. So for example, functions like x squared, a squared, b squared, x cubed are not exponential because the variable is not in the exponent. Whereas functions like e to the x, 2 to the x, b to the 2x, these are exponential because the exponent is varying. Is a variable. The idea is that exponent is a variable. For example, y equals 10 to the x. So when x is 0, 10 to the 0 is 1. Now, this is a general rule that x to the power 0, or maybe not use x, a to the power 0 is 1 as long as a is not equal to 0. When x is 1, 10 to the 1 is 10. When x is 2, 10 squared is 100. X3, y is 10 cubed, which is 1000, and so on. So it's basically repeated multiplication. You're already aware of the properties of exponents from before. Note, recall a bonus problem from exam 2. It gave you a function f such that f of x plus y equals f of x multiplied by f of y. Exponential function, that's the one that satisfied this property. And this is because b to the power x plus y equals b to the x times b to the y by property of exponent. A concept check here. You can verify the above statement, making sure you understand it based on your properties of exponential functions that you have seen before. Graphing an exponential function. Let's start with y equals 2 to the x. First, let's construct a table. Let's start with 0. 0 gives me 2 to the 0, which is 1. This is 2 to the negative 1, which is 1 over 2. 2 to the negative 2, which is 1 over 2 squared, which is 1/4. Again, we are using our knowledge from before where negative exponent we know is reciprocation. 2 to the negative 3 is 1 over 2 cubed, which is 1/8. 2 to the 1 is 2. 2 to the 2 is 4. And 2 cubed is 8. So few observation. It's decreasing here, right? The values. 1/2 is less than 1, 1/4 is less than 1/2, 1/8 is less than 1/4, and it's increasing here. And what does the graph look like? I'd say I let my inputs be 0, 1, 2, 3, -1, -2, -3. Let's say 8 is somewhere here, so halfway is 4, 2, 1, then I have 1/2, 1/4, 1/8. So these points are really close to the axis here. There's 1, 2, 4, 8. If you connect this, it's going to look something like that. It's going to keep on increasing. Now this shape is like it's like a sleeping J. So it's also called a J curve. It kind of looks like a J. Natural base E, just like pi and the golden ratio, which we saw in some of our quadratic equation unit, it's 1 plus root 5 over 2. E is another famous irrational number. The value of E is 2.718281827. It goes on because it's irrational, it doesn't end, there are no patterns. When we use E as the base for the exponential function, that's e to the x, it's called the natural exponential function. Now, how we get E, one interesting way in which we can get E is, if you look at this function, 1 plus 1 over x to the power x. Now, as x increases, we know that this quantity, 1 over x, becomes smaller. Right? So you're adding a very small number to 1, and then you're raising it to that large exponent. So what happens to that? If you plug in some values, play around with the calculator, you will notice the values are increasing, but the rate in which they increase becomes lesser and lesser. So as x keeps on increasing, it settles down to the value, and this value is defined to be e. In compound interest, what happens is when you invest a certain amount of money, which is called the principal, for a certain time with an interest rate r, then you earn some money, and the final amount is given by a equals p times 1 plus r to the power t. And for continuous compounding, it's a equals p e to the power rt, where e is the number we just introduced. So this is one of the applications for the number e. And this is what the banks use because it's continuous compounding, meaning it's the highest possible amount of money you can earn using compound interest. That's the end of this section. We're going to talk about composite functions in the next